In this video, I'm going to explain about the MPLS Traffic Engineering Explicit Path Tunnel. As you can see, we have 5 routers. Router 1, Router 2, Router 3, Router 4, and Router 5. And here you can see that we have 3 paths between Router 1 to Router 5. Blue path, red path, and green path. I configured OSPF as IGP in this scenario. And here you can see the metric of each link. The best path according to the lowest metric is the blue path. As you can see from R1 to R5, the blue path has lowest metric in compare with the red path and also the green path. I can show you. Let me to show you the routing table of the router 1. In router 1, we can use show IP route OSPF. For example, to reach to the loopback 0 interface of router 5 means 192.168.2.545. As you can see here, we use gigabit 00. Why? Because this path has the lowest metric. Also for quad 5/32, another loopback in router 5, and also 5.5.5.50/32, another loopback interface in the router 5. For all of them, in router 1, we have gigabit 00 as the outgoing interface. It means that because the blue path has lowest metric, all traffic between the router 1 to router 5 actually will pass from the blue path. And it means that the red path and also the green path will be empty. And how we can distribute our traffic between these 3 paths. For example, assume that we want to send the traffic of loopback 0 from the blue path, the traffic of loopback 1 of router 5 from the red path, and the traffic of loopback 2 of router 5 from the green path. One of the solutions is using MPLS-TE Explicit Path Tunnel. Actually, we will configure tunnels, for example, one tunnel from the red path and another tunnel from the green path, and then we forward the traffic of loopback 1 from the tunnel of red path and traffic of loopback 2 from the tunnel of green path. Okay, I will show you how you can configure it. Here we have a text file. In the text file, we have some steps. Step 0. IP address configuration and enabling interfaces, and also IGP configuration. You can use OSPF or ISIS for MPLS Traffic Engineering. In this scenario, we are using the OSPF, but in future videos, we will use ISIS. As you can see, I configured this step. Actually, I configured IP addressing and also OSPF and also the enabling interfaces. Here you can see, for example, on the gigabit 00, IP address 10.1.2.1.255.255.255.0, then OSPF configuration, IP OSPF network point-to-point, IP OSPF 1 area quad 0, and also IP OSPF cost 1, because here the metric is 1, and no shutdown. You can check all of the configuration. You can copy this configuration in your scenario. Actually, the step 0 is done. Here we don't have any new feature related to the traffic engineering. Let me go to step 1. In step 1, we start configuration of the MPLS Traffic Engineering. For configuring MPLS Traffic Engineering, we need to do some steps. First, we need to enable MPLS Traffic Engineering globally. Means with MPLS Traffic Engineering tunnels, we should enable this feature on the global configuration mode. You know that for all MPLS functions, the IPsef should enable, and this is enabled by default. Because of that, it is not mandatory to use this command IPsef, but you need to ensure that Ceph is enabled on the iOS. This is by default enabled. But MPLS Traffic Engineering tunnels command should enable, actually should configure. MPLS Traffic-Engineering tunnels. This is by default disabled. And optionally, and also it is recommended to use MPLS label range minimum and maximum for troubleshooting for better understanding the functions. Why? Because if you don't configure MPLS label range, it is possible that all routers use similar labels and it is not so easy to understand what is happening. Because of that, I recommend you that configure MPLS label range. For example, for router 1 between 100 and also 199, it means that R1 you need to choose the labels of MPLS between these two values. In router 2, 200, 299. It means that R2 please choose in this range, and also R3, 300, 399, and so on. But this is not mandatory. This is not related to the traffic engineering. This is related to MPLS. Alright, this is the first step, global MPLS traffic engineering configuration on all routers. Router 1, router 2, router 3, and router 5. Let me to configure this step. We can start from the router 1. Okay, here again, you know that we need to configure it globally, MPLS traffic engineering tunnels on the router 1. Also, MPLS label range 100 between 100 and 199. That's it. The next router 2, MPLS traffic engineering tunnels, okay, global command, and MPLS label range 200, 299. And after that, router 3, here MPLS traffic engineering tunnels, MPLS label range 300, 399. And router 4, again, MPLS traffic engineering tunnels, MPLS label range 400, 499, and finally router 5, MPLS traffic engineering tunnels, MPLS label range 500, 599. That's it. This is the step 1, global configuration, global command of MPLS traffic engineering. Let me go to step 2. In step 2, we should enable traffic engineering or MPLS traffic engineering on the IGP in OSPF or ISIS. Actually, you need to give this capability to the IGP to advertise traffic engineering capabilities or characteristics of each link. Because of that, for example, in router 1 or router 2 or router 3 or 4 or 5, we need to use these commands. MPLS traffic engineering area ID under the router OSPF process. It means that the OSPF now has this capability to advertise the TE or traffic engineering characteristics of each link for area 0. And also, in MPLS traffic engineering, each router has a router ID. This is different than the router ID of OSPF. Actually, this is the router ID in traffic engineering. It is recommended that use the same router ID for OSPF, for example, and also for OSPF for traffic engineering, but it is not mandatory. With these commands, MPLS traffic engineering area ID and MPLS traffic engineering router ID loopback 0, I will configure the IGP for MPLS traffic engineering capability. Don't forget, on all routers we have loopback 0 with this syntax 192.168.254.x. X is the router number. For example, in router 1 I configured 192.168.254.1/32. In router 2, 192.168.254.2/32, and so on. Because of that, we need to configure the TE on IGP in this step. Step 1, we can go to the router OSPF mode, router OSPF 1, and then MPLS traffic engineering for area quad 0, and MPLS traffic engineering router ID loopback 0. That's it. In the router 2, we have similar commands, router OSPF 1, MPLS traffic engineering area quad 0, and MPLS traffic engineering router ID loopback 0. In router 3, router OSPF 1, MPLS traffic engineering, then area, then quad 0, and the next command, MPLS traffic engineering, then router ID loopback 0. The next router is the router 4, router OSPF1, MPLS Traffic Engineering, router ID, loop first area, and then router ID, area quad 0, and MPLS Traffic Engineering, router ID, loopback 0. And the last router is the router 5, router OSPF1, MPLS Traffic Engineering, area quad 0, and MPLS Traffic Engineering, router ID, loopback 0. This is the step 1, step 2 actually, okay? And after that, in the next step, we need to enable traffic engineering on all interfaces. Actually, with these two commands, we can enable traffic engineering on all interfaces. First, on interface, then interface name mode, we need to configure MPLS Traffic Engineering tunnels. This is the first command you need to configure, and the second command is the IP RSVP bandwidth, then maximum reservable bandwidth. With this command, actually, we give this capability to the RSVP or Resource Reservation Protocol to reserve the bandwidth of each link for TE tunnels. For example, in step 3, interface MPLS Traffic Engineering configuration should be done, and the maximum reservable bandwidth is 10 megabit per second. Here we use gigabit interfaces, and gigabit has 1000 megabit per second of bandwidth, but we allow only 10 megabit per second of this 1000 megabit per second reserved by the RSVP. Because of that, in router 1, I use this command. Interface range gigabit 0022 means gigabit 00, gigabit 01, gigabit 02. First, I enable the traffic engineering tunnels on these interfaces, means tunnel can pass from this interface, and also RSVP can reserve up to 10,000 kilobit per second, means 10 megabit per second, okay, on this interface. Let me to show you how we can configure or enable TE on all interfaces of this scenario. In the router 1, interface range gigabit 0022. First command is MPLS Traffic Engineering tunnels and IP RSVP bandwidth, and after that 10,000. Also, if you want, you can use do show IP RSVP interface to monitor the RSVP status on the interface. Look at here. Gigabit 00 RSVP is enabled on this interface, and maximum reservable bandwidth is 10 megabit per second, and until now it is allocated about 0 bit per second. What does it mean? It means that we didn't use any actually bit per second of this interface. I will show you after configuring tunnel what is happening here. The next router is the router 2, this router. Here we have two interfaces. Interface range gigabit 00 to 1. And then MPLS Traffic Engineering tunnels, and then IP RSVP bandwidth 10,000. The next router is router 3, this router. Again, here we have similar condition, interface range gigabit 00 to 1. And MPLS Traffic Engineering tunnels. And after that, MPLS IP RSVP bandwidth 10,000. The next router is router 4. Here interface range, after that gigabit 00 to 1, MPLS Traffic Engineering tunnels, IP RSVP interface or bandwidth 10,000, means 10,000 kilobit per second or 10 megabit per second. Finally, router 5, interface range gigabit 00 to 2, MPLS Traffic Engineering tunnels, and MPLS first IP RSVP bandwidth, and then 10,000. This is the next step that we should do. Until now, we configured the traffic engineering globally with MPLS Traffic Engineering tunnels command, MPLS Traffic ENG tunnels, and after that we enabled the TE or traffic engineering on the IGP, and then we enabled the traffic engineering on all interfaces, and also RSVP enabled on all interfaces. What is the next step? The next step is the step 4. Here we can start to configure the actually two tunnel interface from R1 to R5. The first tunnel should pass from the red pass, and the second tunnel should pass from the actually green pass. I will show you how you can configure it. First, you need to define the two paths that you will use for tunnel interfaces. For example, here we have this command, IP explicit path identifier. Actually, it means that I want to configure this path, for example, red path. And then you need to identify the next hops, or actually the IP addresses that you want to your traffic pass or your tunnel pass from these IP addresses. For example, if you want to send traffic from R1 to R3, then R3 to R5, you can configure next address, okay, next address 10133. This is the IP address of the gigabit 00 of the router 3. And then after that, you should go to the 10355, means the IP address of the gigabit 01 of the router 5. It is easy. Let me to show you here in the router 1. In the router 1, we can configure this command. First, IP explicit path identifier, and after that you need to give it one identifier. Actually, you need to enter a number between 1 to 65,535, for example 10. This is the identifier of this explicit path. Okay, what is the first next hop or next address? From R1 I want to go to the router 3 it means 10133. Okay, next address 10133, that's it. And after that, next address after the router 3 is router 5, 10355. This is the IP address of the gigabit 01 of the router 5. This is our explicit path. If you want, you can monitor it with this command, do show IP explicit path. Do show IP explicit path can show us that the path with identifier 10 has this next address, router 3, and then router 5. Okay, this is the first path. Also, we need another path that should pass from the green lines. Okay, here again you can configure IP explicit path identifier, for example 20, but another method is IP explicit path name and then give it a name. Okay, it means that for identifying your explicit path you have two options. First, identifier with IP explicit path identifier, or name, IP explicit path name, any name. Okay, green, for example. Okay, what is the next address? The next address is router 4, 10.1.4.4, and then next address is 10.4.5.5, means this is the gigabit 02 of router 5. If you want, you can monitor these two paths. Show IP explicit paths can show us we have two explicit paths. First is path 10, next address is router 3, then router 5. Second, path green, next address is router 4 and router 5. Until now, we configured these two paths. Now we need to use them in our MPLS traffic engineering tunnels. Here we can see the commands that we need for configuring traffic engineering tunnels. Look at here. We need to configure two tunnel interface on router 1 to router 5. And tunnel 0's destination is router 5 and tunnel 1 destination is again router 5. Explicit identifier, it means the explicit path for the tunnel 0 is the red path, and the explicit identifier or name of the tunnel 1 is the red path, is the green path. For configuring tunnel, we need to use these commands. Interface and interface name means interface, tunnel, then any number. Okay. We need to assign IP address to this interface. You can assign real IP address to this interface, but in most cases we use IP unnumbered loopback 0, means because this IP address is not so important for us. We enable this IP address only for adding this interface and to the routing table. Because of that, the IP address of this interface really is not used. Because of that, in most cases we use IP unnumbered loopback 0. If you want, you can configure a real IP address. Then tunnel destination. This tunnel destination is very important. Means I want to have a tunnel from router 1 to router 5. After this configuration, the TE try or R1 try to reach to this tunnel destination and reserve the amount of bandwidth or other requirement of this path. And then the tunnel mode should be configured. Tunnel mode, MPLS Traffic Engineering. You know that each tunnel type, each tunnel interface needs to have tunnel mode because we have different tunnel modes. For example, GRAIP, IPsec, other type of tunnel. But this type of tunnel is MPLS Traffic Engineering. And then you need to configure the actually pass method or pass option method. You know that until now we configured the explicit pass, but we have other type of tunnels. You will learn about them in future. For example, dynamic tunnel, for example, semi-dynamic tunnel, but this is explicit pass. You need to configure tunnel MPLS traffic engineering pass option number, and after that you configure explicit, then identifier. For example, the number of identifier means 10 in our scenario. Or here again, explicit name. Look at here. Tunnel MPLS Traffic Engineering Pass Option 1, explicit identifier 10. It means that for this tunnel, the first option, the first pass is the explicit pass I identified, I configured with the identifier of 10. Pass option can help us if we have multiple actually pass for this interface tunnel. For example, you have multiple explicit pass, you say first try this pass, if it is not available use second pass, pass option 2, pass option 3. Okay, don't worry about it for now, but for now we can configure these commands: interface tunnel 0, IP unnumbered loopback 0, tunnel destination, tunnel mode, and tunnel MPLS traffic engineering pass option 1, explicit identifier 10. For the next tunnel that will pass from the green pass, we use these commands: interface tunnel 1, another tunnel, IP unnumbered loopback 0, tunnel destination is same, tunnel mode MPLS traffic engineering, and tunnel MPLS traffic engineering pass option 1, explicit name green. You know that we configured two paths. The first has identifier 10 and the second has identifier or the name of green. For tunnel 0, we use the first pass means the red actually explicit pass, and for this tunnel 1 we use the actually second pass we configured with the name green. It is easy to understand. Let me to configure these two tunnels. We can start from the tunnel 0, interface tunnel 0. First, IP unnumbered loopback 0. Second, tunnel destination is 192.168.2545, means router 5. As you can see, tunnel status is down now. Okay, and then tunnel mode is MPLS Traffic Engineering. And finally, tunnel MPLS Traffic Engineering pass option 1 is explicit pass. Which explicit pass? The explicit pass with identifier 10. Now the tunnel will come up. After some second, you can see tunnel is come up. It's coming up. It means that the tunnel now is working. What happened? R1 tried to actually reserve this pass for this tunnel 0 because we configured the pass from R1 to R3 and R5. R1 sent RSVP message to router 3 and then from router 3 to router 5, and it reserved the pass for this tunnel, and because we reach to the destination or tunnel destination, tunnel comes up. Let me to configure the next tunnel, interface tunnel 1. First, IP unnumbered loopback 0 again, and then tunnel destination is 192.168.2545, and then tunnel mode is MPLS Traffic Engineering, and finally tunnel MPLS Traffic Engineering pass option 1 explicit, but here we use name and then green. If you configure your explicit pass with identifier, you need to say explicit identifier 10. If you configure with the explicit name, you need to configure explicit name instead of identifier, okay? And then the name of pass you define. Again, this tunnel comes up. Let me to show you what happened. With this command, show MPLS traffic engineering tunnels, you can monitor status of your tunnels. Show MPLS traffic engineering tunnels, for example, tunnel 0. I want to see the status of tunnel 0. Okay, here you can see that in R1 we have tunnel 0, and tunnel 0's destination is router 5, 192.168.2545. Administratively, this tunnel is up. You can shut down it, and operationally also is up. Pass is valid, and signaling means RSVP is working correctly. And pass option 1 is the type of this pass option 1 is explicit, and the identifier is 10, and you know what does it mean. And after that, here you can see we have other informations that we will learn about them in future. But for now, you know that the source IP address of this tunnel RSVP signaling info is 192.168.2.541. This is the loopback 0 of router 1, and destination is 192.168.2.545. This is the loopback 0 of router 5. And also the explicit path is from router 3 to router 5, then to the router 5. Okay. And also about the tunnel 1, show MPLS Traffic Engineering tunnel 1. Here you can see that we have another tunnel, R1 tunnel 1. Destination is router 5 or 192.168.2.545. Administratively, this tunnel is up, operational is up, path is valid, signaling is connected, path option 1 type explicit. Now, this is the name of our explicit path. And also, as you can see, the source again is the loopback 0 of router 1, destination is the loopback 0 of router 5, and this is the explicit route we defined, router 4, router 5, and also here we have other information that we will learn about them in future. You can see the uptime is 1 minute and 38 seconds, okay? But if you check the routing table, show IP route, you will see these two tunnels, okay, are not available in the routing table. Actually, when we have traffic engineering tunnels, we need to steer traffic with some method into the traffic engineering tunnels. We have some methods. You will learn about them in future. For now, in the last step, we need to configure two static routes on router 1. For example, we can configure this command. If you want to reach quad 5/32, okay, means in router 1, if you want to reach to this IP loopback quad 5/32, please use tunnel 0. If you want to reach 5.5.5.50/32, please use tunnel 1. With these two commands, IP route quad 5, quad 255, tunnel 0. This is the normal or typical static route, and also IP route 5.5.5.50 quad 255, use tunnel 1. Actually, we are steering traffic into these two tunnel that we configured before. Let me to configure them. Here in the router 1, we can use these two commands. IP route 5.5.5.5 quad 255, please use tunnel 0, and IP route 5.5.5.50, again quad 255, okay, please use tunnel 1. Now we can check the routing table of router 1 with show IP route static command. You will see that here now we have these two static route, and the first static route is for quad 5/32, and it uses the tunnel 0 as outgoing interface, and the second is for 5.5.5.50/32, and it uses the tunnel 1. Now if you check the path, for example, with trace route command, trace route quad 5, okay, numeric, can show us traffic will go to the router 3 and then router 5. And if you check, means from the green path, okay, green path means router 3, and actually red path from router 3 to router 5. And again, trace route to 5.5.5.50, again numeric, you will see traffic will go to the router 4 and then router 5. Okay, and for example 192.168.2.545, because we didn't configure any tunnel or any static route, traffic will go from the base path according to the IGP, means the blue path. Trace route 192.168.2.545, okay, traffic will go to the router 2 and then router 5. What does it mean? We distributed traffic. With traffic engineering, we distributed traffic of some of traffic of router 5 from the blue path, some other from the red path, and some other from the green path. Okay, this is in this scenario, we learned two important things. First, explicit path configuration for TE, explicit path, but we will have another methods. I will explain about them in future. And also, we learned about how we can steer traffic into the traffic engineering tunnels. In this scenario, we learned about the static method, because we configured a static route for steering traffic into the traffic engineering tunnels. All right. Also, if you want, you can check the routing tables to see, or the maybe LFIB to see the labels. For example, you know that when we reserve the pass from router 1 to router 5, RSVP actually should bring us label. You send RSVP pass message to router 3, then router 5. When router 5 accept the pass, okay, it should send a label to router 3, and then router 3 another label to the router 1. Because router 5 connected to the destination, it will send pop label or null label to the router 3, and router 3 will allocate its label and then send it to the router 5. For example, if you check show IP ceph and then to quad 5, quad 255, this is the label received from the actually router 3. Here you can use internal. You will see label 300 received from the router 3 in the router 1. And in router 3, if you check show MPLS forwarding table, this is the command that we use for monitoring the LFIB or label forwarding information based, you will see that the label 3, if router 3 receive label 300, it will pop it and send it to the gigabit 01. Okay, it means that you send traffic from R1 to R3 with label 300, the router 3 should pop this label and forward the traffic to the router 5. And here you can see this happened before with the traceroute command. Look at here, router, we used traceroute to quad 5, traffic went to the router 3 with the label 300, and after popping the label, the traffic will forward to router 5. Also, for the next destination 5.5.5.50, if you check show IP ceph again for this network, you will see that we have label 400 received from the router 4, okay? And in router 4, if you check the show MPLS forwarding table, you will see that the label 400 will pop and traffic will forward it to the from the gigabit 01 to the next stop router 5. And here in router 1, you can see this has happened before with traceroute quad 5.5.5.50. This is the command we used, okay? Label 400 received, sent to the router 4, and from router 4, after popping the label to the router 5. This is the first method of configuring tunnels in traffic engineering. But in future videos, I will show you how you can configure traffic engineering tunnel with dynamic method and also with semi-dynamic tunnel. Don't forget, you need to configure this scenario, and according to the text file, in text file we have some steps, step 0, step 1, step 2. You need to configure this scenario, and after that you will be ready for learning the next method of traffic engineering tunnel configuration, dynamic path tunnel.